All right. Thanks, everyone, for being here. Thanks to ARM for giving us the opportunity to talk about Mekonos and kind of what we're doing over there. My name is Anil Narasimha. I'm the CEO and co-founder of Mekonos. We are Bay Area based. And what we're really trying to do is develop a new modality of delivery of payloads, molecules into cells. Really creating a universal platform, being agnostic to the payload and agnostic to the cell type. And the way we're actually doing that is by utilizing controllable nanoneedles to really drive that single cell level precision of delivery that I'll talk about. I like to start out with kind of like a thought exercise that I'm sure some of you guys are thinking about is, what if you could transfect any fragile cell with high viability, with high efficiency, obviously kind of number one goal. You can do large multiplex payloads, meaning delivering multiple payloads at the same time into cells, CRISPR editing being a prominent application of that, at single cell level precision, right? So we're not talking about a population of cells, but we're talking about kind of each individual cell as its own entity. With unprecedented control, meaning can you start even controlling the amount of payload or amount of cargo that goes into a single cell. And so we at Mekonos have data actually supporting a lot of this, really demonstrating delivery into a variety of different fragile cell types, whether it's immune cells, stem cells, and other primary cell types. And our standards are really high, meaning at least 95% cell viability and at least 70% efficiency of whatever you're delivering and into whatever cell type that you're working with. Loading multiple cargoes up to 100 kb. One of the cons of viral vectors is you're limited about the amount of genetic material that you're putting in, whether it's AAVs or lentiviruses, and so we don't necessarily have those restrictions. And then I was mentioning the nanoneedles, but the cool thing with our technology is the fact that we have one needle into one cell, and so we're very deterministic in our approach to be a true single cell level platform. And then this idea of finely tuned dose control, meaning controlling the amount of payload that goes into a single cell, and then targeted delivery too, right? Let's say you want to deliver directly into the nucleus, and then so that's a capability that we have. And so what we're really trying to create is really building a future of cell therapies on a chip. And so we're creating this cell engineering platform, really taking advantage of silicon technology to create what we call a hyper-precise ex vivo delivery of any type of molecule into any type of cells. And so how does the technology work? You can think of our platform as kind of bringing three core technologies together and working synergistically. Number one is a chip that we've developed that has controllable nanoneedles. So we utilize MEMS technology to have that actuated kind of needles that can kind of deliver and be the mechanism of how you're delivering a molecule or a cargo into a cell. The second technology is a cell trapping chip that utilizes microfluidics technology that traps single cells into specific nodes. And so what you do is you pair the needle chip with the cell trapping chip, and what you get is single cell level injection, but massively parallelized. The analogy is something like IVF or even atomic force microscopy, where for those kind of applications, you're doing kind of one cell at a time. So picture that, shrink it down, and instead of one cell at a time, you're doing millions of cells at the same time. And then the third kind of technology that really ties the room together is a patented surface chemistry that we have that facilitates attraction of a payload and then release of the payload once the needle is inside the cell. The needles that we fabricate are not hollow, so the payload doesn't go through the needle for a variety of reasons, mainly because manufacturing those is much harder, like those hollow structures, as well as they become more brittle if they don't have as much mass, as much mass. And so we went the solid needle route, and so we had to develop a surface chemistry that basically facilitates attraction of any type of payload. And then once the needle is inside the cell, we take advantage of the cell's internal environment to release the payload of interest. And so how does the cell poking work? How does the workflow work, right? So into our system and into our box, you flow cells in, they get trapped into these cell trapping sites. And then you align the needle chip with the cell trapping chip, and so you get that one needle to one cell. So one needle is not going into more cells or or multiple needles into one cell or anything like that. It's one needle to one cell. And that's why that alignment piece is so critical. And then the other cool thing is the chemistry that we've developed is just a dipping mechanism on the needle itself. So you dip your needle chip with into the buffer, into the solution that houses your payload, and then you're ready to poke. So then the needle comes down and pokes the cells, and then you can collect the cells and for whatever application that you want downstream, whether that's immediate analysis or expansion or whatever the application warrants. And so our vision really is to create a scalable manufacturing platform. The cool thing is we're going to have the ability to really parallelize chips to really increase throughput. And so we can really get millions of needles at the same time. But the key thing for us is the user experience, right? Can you develop a platform that's easy for the customer to use, and where you don't need so many bells and whistles to create kind of the data that you want. And so what we really kind of look at is what is the opportunity map for a company like ours, right? Because we're coming out with this kind of different modality, right? Nanoneedle injection of payloads, right? You've heard of, obviously, viral vectors and electroporation, but what do we bring in terms of unique capabilities? So I think we all understand the challenges of viral vectors, especially on the manufacturing side: time, cost. There's limitations in cargo capacity. I think just manufacturing logistics is very, very challenging. On the other hand, electroporation, you might have better. You might be a little better in terms of some of the manufacturing challenges that you have, but viability always remains a concern. I mean, think about you're zapping cells with an electric field, right? And a lot of cells are just not going to like that. You're either going to get compromised in functionality or you're going to get compromised in viability, which both are not good things. And so what we really want to create is this idea, this kind of gentle approach to primary cells specifically, right? Immune cells or stem cells. I've talked a little bit about some of the other unique capabilities that we bring, but I think the key kind of high-level takeaway is we're a single cell level platform, right? So which means that we have controllability at that single cell level, which I think is kind of places us in this unique space in terms of delivery. Because I think all the other strategies that you see, whether it's electroporation or viral vectors, they're population-based strategies, so you don't have that single cell level control. And so what we're really trying to create or trying to develop is, how do you unlock opportunities with kind of this idea of single cell level delivery? We've kind of really been focused on our partnerships, and some of these partnerships are with specific applications, and that includes kind of intra-needle multiplexing, meaning delivering multiple components or multiple cargoes at the same time for advanced gene editing. iPSCs, as many of you know, are notorious for being very difficult to manipulate, to engineer, and so we have a number of data sets around editing efficiency and viability in iPSCs specifically. Earlier this year, we announced a partnership with BitBio. I think BitBio's here as well, kind of really working and being a true enabling technology for their iPSC programs. Sequential editing, one of the downsides of electroporation is there's a recovery period, right? It's usually 48 to 72 hours, because think about how many pores are being created on the cell membrane. For us, we're only creating one pore, right? Because we're very deterministic about our approach. So what does that mean? That means the recovery time is basically nothing, right? Let's say 1 hour max. And so you can do sequential editing, especially kind of for safety benefits to prevent genomic instability and things like that. Large payloads I was talking about earlier, there's not really a limit to how big the payload can be. I'm sure, if you're trying to deliver like, I don't know, a piece of hair or something into a cell, it's not going to work. But we have the ability to deliver, much greater than what a lentivirus can hold, as an example, right? I think it's like 11 or 12 kb. So we can do much more than almost 10x that. And then better data packages. I mean, think about because we're at that single cell level, we can have data on each cell, right? So moving forward, especially as we get into manufacturing, those data packages become that much more clean, that much more kind of specific to whatever application that you're doing. And just kind of high-level data that I'm happy to show is, multiplexing payloads. So in T cells right here, we have a plasmid that expresses GFP and a plasmid that expresses mCherry. and most of the cells get both, right? And the cool thing that I'm not demonstrating here, but that we have the ability to do is kind of change the ratios, the stoichiometries of each multiple payloads. So especially for like iPSC reprogramming is a good application for what, something that we can do pretty well. Dose control, right? So like in this particular experiment, we can kind of keep everything the same and just change one parameter, that either being the input concentration, meaning the starting concentration of the payload, the residence time of the needle, because you can imagine the longer time the needle stays in the cell, the more payload that's going to get released, and the depth of penetration. So these nanoneedles are about 15, 20 microns in length. And so you can, instead of going 2 microns into a cell, maybe you go 5 microns and you get more access to payload. So all of those are totally controllable in our system, and you can kind of create kind of this idea of relative dose control. I wish we could do something like delivery 472 molecules of X, maybe in another iteration of the platform, but we can be really kind of relative in terms of controlling the amount of payload that goes into a single cell. We can do RNP deliveries. Compared to nucleofection here, we have much higher % reduction as well as higher viability. And then large plasmids, right? This is just an example of a 15 kb plasmid where we compare to lipofectamine, and we get much higher efficiency and viability as well. And there's way more data sets that we have that we're happy to share, especially for folks that are interested in working with us, including in kind of in an immune iPSC niche, nuclear delivery, mRNA. There's a lot of things that we can do, and not very many things that we cannot do. For us specifically as a company, what our goal right now as we move into 2023, or as we move into 2024, is to really deploy our RUO instrument, what we're calling ARC, to our select partners, and really expand upon those. And then the goal for us in the upcoming is to like create a GMP product, which we're on the way to doing as well. So with that. I'd like to thank first our scientific advisory board. I think we have a world-class scientific advisory board. Irv Weissman, who's one of the godfathers of stem cell biology. Carolyn Bertozzi, who's actually really helped us on the surface chemistry side. She won the Nobel Prize last year. And then Cassian Yee, who's Parker Fellow at MD Anderson. We have a phenomenal leadership team. Ben and Jake are actually here attending the conference as well. So if you're sticking around, I think we'll be here for a while. So happy to chat with any folks that are interested in learning more about our technology. Our goal as a company is to really, cultivate these partnerships, create, obviously expand on the current ones that we have, but also create new ones too. So that's why a conference like this works wonders for us. So looking forward to those conversations. And with that, I guess I have 2 minutes left. If there's any questions, I'd happy to answer them. Thank you. Yeah, sure.
Here you go.
Sorry?
When are you planning to? Oh, there we go. I got the cube. When are you planning to go to commercial?
Yeah, so for our first product, the idea is going commercial next year.
Next year?
Yeah.
Okay.
Yeah.
Beginning, end? With...
Well, it kind of depends on what the application is, but let's say mid next year.
Okay. Anybody else want the cube?
Yeah.
What's the throughput in number of cells?
Yeah.
There's an advantage for one cell, and that might be millions for
Yeah, for sure. So right now, each chip, a single chip has about 250,000 needles on it. So the key thing for us right now is we have the ability to parallelize chips, and we're trying to figure out how many we can. But the parallelization allows us to get into the numbers of tens of millions at least. Yeah. Cool. Thank you.